Well, here's a fairly challenging example problem involving the law of conservation of energy. It looks simple enough, it seems straightforward. In this case, we have a block with a mass of 5 kilograms, and it's dropped from a height of 3 centimeters above a platform connected to an ideal spring. And that spring has a stiffness of 4,000 newtons per meter. Just to make the math easier, let's round up and let G equal 10 meters per second squared. This is not a laboratory investigation, so precision in measurement is not an issue. So when I say this seems easy enough, well, first question is just how far will the spring compress? This obviously somehow involves law of conservation of energy, right? We're going to convert some gravitational potential energy into elastic potential energy. The second part of the question is, what's the maximum speed of the block? Okay, so let's take it one step at a time and answer question A, how far will the spring compress? So let's label position A. Now, good problem solving involves sort of putting yourself into the picture, animating and visualizing what this is going to look like. So we'll extend the drawing and we'll picture the spring when it's at its maximum compression, which implies that the velocity of the block has once again reached zero. After all, if the block were still traveling downward, then it would still be compressing the spring. So at maximum compression, the velocity is zero. So now we have a position B that we can label in our picture, and we can further label it by adding a symbol, we'll call it X in this case, to represent how far the spring is compressed. And let's add D plus X together to label some value that we'll consider H. Okay, so the energy at point A and the energy at point B have to be equal. So the energy at point A, well, the block's at rest, kinetic energy is zero. The spring is not yet compressed, so there's no elastic potential energy, but there is gravitational potential energy at point A. So we're going to say mgh equals, okay, then at point B, again, the block is at rest, kinetic energy is zero, and we set a reference level of h equals 0 at this point, which is why we're calling h the combination of d plus x. Right, so gravitational potential energy is 0, but we do have some elastic potential energy. So mgh equals, I know you're tempted here to say 1/2 k x squared. Let's double check and make sure that's right. Yeah, exactly. X is the distance that the spring has been compressed. Okay, do we say plus Q? Well, if we had to account for the effective air resistance or the forces involved in deforming the spring if it was non-ideal, yeah, we'd have to account for it. But in this case, we're going to make the assumption that mechanical energy is conserved. So this seems like it should be very easy, except X is incorporated into the value of H. So we need to make a substitution. mg times the quantity d plus x is equal to 1/2 k x squared. Okay, step 3. mgd plus mgx equals 1/2 k x squared. So this is a bit of a challenge only because we have an x to the first power and we have an x squared term. So we're going to have to use the quadratic formula. We'll put it in the form 1/2 kx squared minus mgx minus mgd equals 0. So it looks more like ax squared plus bx plus c equals 0. And we know the solution in that case, x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So if we make the comparison here, notice we don't have to plug in any numerical values. It's good to keep everything algebraic until the final step. So this means x would be equal to mg plus or minus the square root of the quantity mg squared. Well, I suppose technically negative mg squared, but a negative value squared is positive. Okay, minus 4ac, that's going to give us plus 2k mgd. And all that divided by 2a, so all of that then divided by k, right? A is 1/2 k, so 2a would be k. All right. Well, let's see what we get here. That means x is equal to, we can't really simplify this any further, so we'll plug in some numerical values. But let's take it a step further and consider the special case where d is equal to 0. In other words, instead of dropping the block from a height above the spring, what if we place the block on the spring and then let it go? It's going to compress it, and we have to figure out what total distance. Well, if d is equal to 0, which is not the case that this problem started out as, but just to check to see if our final answer is reasonable, let's consider this special case. Then x would be equal to mg plus or minus, let's see, this whole term would go to 0, right? So it would have mg plus or minus the square root of mg squared. Well, that's silly. That's just the same as saying mg plus or minus mg all divided by k. And we know the answer is definitely not x equals 0. So it looks like x would be equal to 2mg over k. Now, what does that mean? Well, let's animate this picture one more time. So there's case A, and then eventually the spring is fully compressed. There's condition B, but we ignored is there's some point in between, right? And I want you to consider a free body diagram. In this case, the forces on the spring are 0. In this case, there's a force mg that's down. The force in the upward direction is greater than mg because we know at this instant in time that the block would have an upward acceleration. It would want to rebound back up. But at this point, somewhere in between point A and point B, that's when the forces would be in equilibrium. So there'd be some value k, maybe we'll call it x naught, and mg. Okay, so that means there's a value of x naught that's equal to mg over k. So it looks like this is telling us that the value of x, if we release it from rest right here, would be equal to 2 times x naught. In other words, the distance that it displaces until it reaches equilibrium gets it halfway to its final resting place where the velocity would momentarily be 0, and then it accelerates back up, passes back through this equilibrium position for a moment, and then returns back to this point. So I just thought I'd share that with you as a little bit of insight of the behavior of an ideal spring. Of course, this is not the case that we're working with. We're not just letting the block go from a state of rest on the top of the spring. It actually begins 3 meters above the top of the spring. So if we want a numerical answer in this case, we'll apply this formula and see what we get. We would get x equals 50 newtons plus or minus the square root of 50 newtons squared. Remember, it was a 5 kilogram object, and we're letting G equal 10, plus 2 times 4,000 times 50 times 0.03. And I suppose this is going to give us square newtons, all divided by 4,000 newtons per meter. Now, if we check the units, everything under the radical sign is going to be square newtons. So the square root of newton squared is newtons, and newtons added with newtons divided by newtons per meter is indeed going to give us meters. So the units will work out. Grab a calculator and see what you get. Okay, so we get the square root of 2,500 plus 12,000. So this gives us 120.4, and we need to add 50 to that. It gives us 170.4, and we need to divide all that by 4,000. So it comes out to be 4.26 centimeters. Okay, that was a lot of work just to get the answer to part A of what seems like a very straightforward problem. I think maybe part of the reason it took so much work is there's a lot of mathematical computation when using the quadratic formula, and we also wanted to take a deeper investigation into what this derived formula is telling us in the special case where D is equal to 0. Well, let's solve part B. What's the maximum speed? Here's where I find a lot of mistakes. This is a problem that's typical of a course like this, and I review this problem every semester, and I find that a lot of my students are tempted to say that the maximum velocity occurs at the very moment that the block first makes contact with this spring. Gravitational potential energy is being converted into kinetic energy, and so most people think that then as soon as the spring starts to engage, then that kinetic energy has to start to convert to elastic potential energy, and so from that point on, the kinetic energy is going to start to decrease. That discounts the fact that as the spring compresses and the elastic potential energy goes up, not only is kinetic energy decreasing, but there's more additional gravitational potential energy being tapped into. So a better way to consider this is to think about Newton's laws. So the forces acting on the block when it's right here at very first contact with the platform is just mg. There's no value of kx in the opposite direction yet because there's no compression of the spring yet. Okay, then the block reaches this point, and now there's some compression. Although not a whole lot of compression, so the force kx might still be a little bit smaller than the force mg. So that means it's still accelerating downward. And if it's accelerating downward, its speed has not yet reached its maximum value. Now the block's going to fall a little farther and get here. And perhaps at that point, then kx and mg are equal in magnitude. So for a moment, acceleration is equal to 0, and that's when you have the maximum value of velocity. Now from there on, the block is going to continue to fall, and the free body diagram will show that the force in the spring is actually greater in magnitude than mg. So from this point onward, the block continues to descend lower and lower, but is slowing down as it does so. So the block slows down over the last few centimeters of its displacement, but it's still speeding up for the first few centimeters after first contact is made. So the temptation might be to say that I've considered cases where potential energy, gravitational potential energy that is converted to kinetic energy, and I find time and time again, having done enough practice, that that always gives the result V equals the square root of 2gh. H is just 3 centimeters as given in this problem, so this should be very easy. No, no, no. H is not 3 centimeters. It's 3 centimeters until it first makes contact with the platform, but the block's going to continue to descend a little farther until the free body diagram looks like this. So we're going to label this actually as x naught. So we can say in case A, the block is 3 centimeters above the platform. In case B, the block comes to rest and the platform is fully compressed, but at some point in between, the free body diagram reveals equilibrium. So if we want to call this value x that we solved for in part A of this problem and found an answer of 4.26 centimeters, if we've already labeled that as x, then we can't label this as x. We label it as x naught. And so the total height the object falls until it gets to that point is 3 centimeters plus x naught. And so if we compare energies from point A to this, what do we call it, just special point, then the energy we have here is gravitational potential energy. And the energy at this special point is kinetic, where this V then would represent the maximum value, plus, what else? Well, the spring is compressed a distance of x naught, so there's some elastic potential energy as well, 1/2 k times the quantity x naught squared. Well, we're free to set our reference level wherever we want to, so why don't we move the reference level in this case up to this point? Okay, then there's no gravitational potential energy when it gets to this point, and then the value of h will indeed be x naught plus 3 centimeters. We can keep it all algebraic though. 3 centimeters already has a label given to it. We were calling that d. So mg times x naught plus d is equal to 1/2 mv squared plus 1/2 k times x naught squared. But I want to substitute for k. Now, what can I substitute for k? Based on this free body diagram, we can say k is equal to mg over x naught. Well, wait a minute. Maybe we want to do that the other way around. Maybe instead of substituting in place of k, we want to substitute in place of x naught. How about that? We know the k value. All right. So we're going to substitute in place of x naught an expression mg over k. All right, so this gives us an expression 1/2 mv squared is equal to mg times d plus mg over k minus 1/2 k times mg quantity squared over k squared. Well, I'll let you do some of the algebra. There's a step 4, step 5, step 6. We'll see how many steps it takes. But I'll show you the result you should end up with. You should ultimately arrive at an algebraic expression that says v squared is equal to g times the quantity 2d plus mg over k. So I'll let you hit pause right now, and you can go through all of the algebra required in an attempt to verify that this is the correct result. And after you get there, then you can unpause and watch the rest of the video. So hit pause now, do the algebra on your own note paper. Okay, welcome back. So glad to see that you got the same result that I got. Now let's think about exactly what this implies. So let's consider some special cases again. What if d is equal to 0? In other words, instead of dropping the block from some height onto the platform, what if we took the block, gently placed it from a state of rest, and let it go? Then of course it's going to compress some distance, right? If d is equal to 0, then the maximum speed occurs at the equilibrium position, and that maximum speed then would just be equal to the square root of m over k times the quantity g. Okay, what if k approaches infinity? What if it's an incredibly stiff spring? Well then, this term right here, mg over k, would go to 0, and then we would find v is the square root of 2gd. This is a very familiar result, right? That's what happens when you convert gravitational potential energy into kinetic energy. In other words, if the spring was ridiculously stiff, then when the block is dropped from 3 centimeters and first hits it, well, if it's ridiculously stiff, it's not going to compress any further from there. And then this really would be the case where gravitational potential energy is converted into kinetic energy, and we should get this result. Okay, but the actual result we get when d is not 0 and k is not infinite is this value. And if we want to plug in the numerical values described in this problem, ignoring these what-ifs, then our maximum velocity would be equal to 10 times 2 times 0.03 plus 50 divided by 4,000. Reach for a calculator. Oh, I'm sorry, it would be the square root of all that. And we get a velocity of about 0.85 meters per second. Now let's compare that, by the way, to the velocity that the block has at the moment it first makes contact with the top of the spring. Then v should just be the square root of 2gd, which would be the square root of 2 times 10 times 0.03. And this gives us a value, v naught, we'll call it, equal to 0.77 meters per second. Okay, how could we make this problem even more involved, even more rigorous? Instead of dropping an object vertically, what if we were told that we put an object along an incline and allowed it to slide and make contact with the block, or make contact with the spring, sorry. If the question is, where does the object have its maximum velocity? Don't get suckered into saying that it happens right here. we know the spring is going to continue to compress until it reaches an equilibrium point, and so max velocity would actually be here. And that's not the point of maximum compression. It would continue to compress even further, and the block would ultimately come to rest here. So if the question is how far does it compress, we can solve that. You'd probably have to use a quadratic formula, and you're going to have to do a little bit of trigonometry to break vectors into components, or at least to consider how you can measure height based on length and angle. How could we make the problem even trickier? Well, we could say that there's some value of mu that's non-zero in this case. So hopefully you encounter some versions of this problem which will challenge you even further as you work through your homework or solve some of the assigned AP problems. That's a long video. That's a lot to take in, both mathematically and conceptually. Feel free to rewind, replay, and ask questions. And as always, thanks for watching.